a quick intro about myself. My name's Karan. Previously, I was working as an SD at Dell Technologies. We had like a few projects that wanted a bit more analytics that slowly led into predictive analytics. And that essentially sparked my curiosity into machine learning. I later did my master's in data science from CMU and then worked at Amazon as an applied scientist. Recently switched to Walmart as a senior data scientist. And yeah, bit of a content creator on LinkedIn, an audience of 55K, and I do a bit of mentoring on TopMate and via BuildML. I'll share the slides afterwards so you can check out all these resources. And most of the resources that I'll be mentioning on the talk as well, you can check them out via the slides. So, coming quickly to what I had in mind for today's session. It was going to be like a quick overview of recommender systems, the past of recommender systems, what it currently looks like today, and a quick overview of the key research areas that most of us in the industry are working on in terms of like a future looking slide. Maybe just a like a very the history of recommender systems should hopefully cover a basic idea, but to give like a immediate idea, recommender systems, when you log on to Netflix, you get like recommendations of movies coming onto your screen. So what algorithms powers those? That's what we call as recommendation systems. The When I'm covering the history, you'll get a hopefully a better idea about how these came to be and what problems they're solving. But in case there are any questions, I'll pause in between certain slides and feel free to ask questions on the chat as well. Hopefully that works. Um,
Yeah,
yep, awesome. So, how exactly did recommendation systems start, or what user problem motivated this field? So, around 70s and 80s, the internet was essentially gaining a lot of momentum. A lot of information was available at the hands of users. So, as a result of increase in information, a user problem came into existence, which is how do I find content that is relevant to me as quickly as possible. Now, initially, this was solved by search and retrieval, where the idea was users would provide the input of what content they want, and the system would try and find a solution for it. And a lot of search systems came. Google came in like the late 90s, and it started dominating. So now, search and retrieval was targeted at helping users discover things that they want. Now, a group of users were also working on a branch of this problem, which is that, hey, we know what kind of different information users interact with, or products and services that they interact with on the website. Now, knowing this, can we push or promote stuff that they might like, and can that be sort of a commercial product that can be released? Now, two main groups that sort of worked on this and showed that this is a commercially viable, and not just commercially viable but very lucrative playground, was Tapestry in 1992. They sort of developed this news recommendation system. There was a research group called Group Lens. They released this product called Tapestry, which is a news recommendation system. It was essentially based on collaborative filtering. What is collaborative filtering? We'll be covering in a bit. But essentially, it provided news recommendations, and it worked out very well. Then again, around the same time in 93, MIT Media Lab released a solution called Ringo, where essentially based on sales of music CDs, they could provide recommendations to users about what kind of music they might like. So this is a sort of like this discovery part that didn't exist till that point in time, and that discovery part had a lot of commercial potential, and that sort of led to the growth and interest in recommendation systems. Hopefully that gives a good idea about or what motivated recommendation systems. Now, coming to the foundations of recommendation systems, or sort of like recommendation systems as it was about a decade ago, what we also call like the first gen recommendation systems. So, a quick sort of division, they're basically divided into three. The first one, or the most easiest one to implement, is called content based filtering recommender systems. So these recommender systems essentially recommend items which are similar to items that the user has seen before or used before or bought before. Now, what do I mean by similar? Any item has a certain set of attributes. For instance, if you're buying clothing, it could be a certain brand, it could be a certain style, like Oxford shirts or t-shirts, stuff like that. So every item has a certain attribute, and you would be recommended items which have similar attributes based on the attribute level criteria. So that's how content based filtering works. Now, there are different types of content based filtering you can build out. The simplest one is demographic based. Like if you create a new Instagram account, and if you just go to the explore page, it'll start providing recommendation based on which geo you're located, and what's popular in that geo. So that's a simple demographic filter. Netflix also does this. You log in via Netflix US, it's a different recommendation set that you get. If you log into Netflix India, it's a different recommendation set that you get. Now, another type of content-based filtering is utility-based filtering. This is more common in websites like Mintra, where whenever you buy a certain product, those products have certain attributes. So, for instance, if you're buying a shirt, if you tend to buy shirts that are blue in color or formal shirts, then those attributes are understood by the system, and it sort of gives you more recommendations based on that. So, based more on what we call utility or item level attribute. Demographic is a bit more towards like who the user is, because the geo stuff like that, that's more user specific, and you filter based on that. Utility is based on more item level attributes.
No, no, no. You
The
can't.
next level of access is knowledge based. Knowledge based, the user can use a huge number of filters and input to figure out, to provide or filter down to what they actually want, and those filters are then used from then on to provide recommendations. Mintra is a great site which has its filters very well configured, which shown on like the right hand side image. And yeah, those filters that you use most frequently, they themselves feed into the recommendation system to act like a knowledge based filter, because they understand that okay, these are the conditions for the recommendation system to work. So this is like a very simple way of building a content based filtering system. Another type of recommendation system is the collaborative filtering one. This was the one that actually revolutionized the space like a decade back. So, what is the intuition behind a collaborative filtering system? The idea is what a user likes. If you can find similar users in your in your user group, if you can find a user who's similar to this user, similar in taste or preference, then whatever that user like, you can just recommend to this user. That's the essential intuition behind collaborative filtering. How do we achieve that? There are two main ways of achieving collaborative filtering. One is the memory based way, and the other is the model based way. So, how does the memory based way work? If we take this example, for instance, let's take user C and user A. So user C and A have rated a particular, let's assume that this is on the row we have users, and on the column we have, let's say, movies. So user C has rated a particular movie 4, user A a particular movie 5. Similarly, they have both disliked a movie. They have rated movie 4 both as 1, and movie 6 both as 2. So it can be sort of hypothesized that these two users are somewhat similar in their taste or preference. So based on that, if since user C has liked movie 2 a lot, probably user A will also like movie 2 a lot. So that's the essential idea behind this memory based collaborative filtering approach. How it works is using simple cosine similarity. So if you have a vector, you understand how to measure the similarity between two vectors, right? Like how to ensure that the distance between, or how to measure the distance between two vectors. Cosine similarity is one way. That can be simpler methods like Euclidean, but cosine is the most commonly used. So if the similarity is higher, you would prefer to select those users as the similar users and recommend what they have liked to this particular user or the user in question. So that's one way of doing it. There is another form within memory based, which is called item similarity. It works very similarly to user similarity. I'll cover that a bit later. But for now, just remember, the idea is you want to find users that are similar in taste to the user in question. Now we covered memory based. There is also another way, which is model based collaborative filtering. So again, coming back to our metrics where we have users on the rows and movies on the columns. So now this metrics, like we know based on vector algebra, that this metrics can be decomposed into two other matrices, like with where this matrix A has the same number of rows as the original matrix, and matrix B has the same number of columns as the original matrix. So if we multiply these two matrices, we'll get the same matrix back. So that's the intuition behind model based collaborative filtering. The idea is we will create two matrices with the same, so such that its dimensions meet this output matrix. We will randomly initialize the values in these two matrices, and then we will optimize so that when they are multiplied and we get this resultant matrix, the rating that this resultant matrix provides will match the rating in the original matrix. So you want to provide, or you want to reduce the error as much as possible. It's done by an algorithm very similar to gradient descent. In this, we call it alternating least squares, but it's very similar. You initialize, just like in gradient descent, you initialize your vector, you have your output that you want to reach, and you're essentially trying to reduce the error by a recursive algorithm. Now, we covered one which was content based filtering. The other one was collaborative filtering, the other type of recommendation system. Now, what are the pros and cons when to use which? Content based collaborative filtering is really good as a starter recommendation system because it works on attributes, user attributes or item attributes. So if you can get some of them, you'll be able to provide recommendations. Whereas collaborative filtering doesn't really work unless you have this kind of interaction history. That is, what has the user liked before, or what kind of ratings have has a certain item received. Those kind of interactions, if you don't have, it's really hard to make recommendations. This is also very commonly referred to as the cold start problem in recommender systems. And a cold start is sort of a drawback of collaborative filtering, but not for content based. However, content based, you need to have the attributes, and you as a designer of a recommendation algorithm need to specify which attributes you are going to focus on, which is again a bit of manual work. And that is sort of the one of the key drawbacks of content based filtering. So now we have a clear idea about recommendation systems. We have content based, we have collaborating, and we have the third type, which is nothing but putting content based and collaborating together, which is the recommendation score that you finally provide will be powered by both a content based system and a collaborative system. So you can use both. That way, if in case you don't have a lot of user interaction history, you can rely more on the content based one. If you have that, you can rely more on the collaborative filtering based one. Now, if anybody's interested in getting started with code or anything, I have like linked tutorials and Kaggle resources that you can use to get started. But just in case, I'll take a quick pause in case there are any questions before moving to the next section.
Yes, so guys, board is open for the questions. If you guys have any questions so far, some of you
Uh,
might be were asking questions. You can just come ahead.
sure. Cool. Now, coming to the next sort of key thing that we just need to discuss slightly, just so that we understand recommendation systems a bit better, is the metrics in recommender systems.
Karun, I guess one guy has a question. Vishal, should
Yeah,
have.
there was this question asked in
Uh,
chat section only. Yeah, this is, I mean, this must be done through the deep learning algorithms. Is it true?
so yeah, right now we are talking about the first gen recommender systems, that it's more a bit of metrics factorization and alternating least squares. So a lot of that is more recursive algorithms and linear algebra. But yes, second gen, third gen will be covering more DL based methods. And yeah, current SOTA in recommender systems definitely deep learning based.
Yeah, Akash, you can just ask your question again.
Uh, Hello, Karan. Yeah, so since we are talking about deep learning here as well, I have this question like back in few years, machine learning works where I mean it was very much needed, but now there were a lot of good works that we can do with deep learning. So how much like machine learning is still relevant, or like we have completely switched to deep learning now?
Um, DL is just basically a technique, specialized technique within like the broader umbrella of ML. So the basic principles within ML still continue to exist. If you're talking about are neural networks the only type of model that powers recommender systems? No. Um, Content-based filtering is still quite effective when you're building out an initial recommendation system. Like let's say you're a new company, you have no user interaction data, so you have no idea of what recommendations to provide. In that case, just content-based filtering, looking at the attributes and filtering out based on those attributes and providing recommendations, that still works. A few of the carousels in your Netflix is actually still powered by content-based recommendations. In Spotify, still powered by content-based recommendations. So it's not fully DL dominated, but yes, your YouTube recommendations definitely have like DL models powering them. So some carousels, sure, there could be like content-based, but majority of your site, more or less, could be powered by DL. But yeah, metrics factorization is also quite powerful. It really depends site to site, I would say.
Okay, okay.
Yep. So it really depends upon the scale at which you work. Metrics factorization starts showing its value when you have a huge amount of data. So for instance, if the situation you're describing is like, okay, it's a new movie usually is going to be pushed a bit more by certain business logic. Like for instance, a new item on an e-commerce platform, let's say on a Marvel movie is going to be released on Netflix. There is certain business logic that's going to try and push the movie more, like within like top 10 trending, some sections like that, so that you can bring more users in. That is one way to treat this cold start. The other way is if a bit more attribute based, like if you know that the user is like a Marvel fan, then based on that attribute you might be able to connect to the movie and push the movie more. But the metrics factorization is a bit more effective, especially in case of new items, new users, when you start getting like a decent amount of data on them. Yeah, a metrics factorization definitely is capable of handling any kind of missing values. As long as like you have enough users, enough items, and enough interaction data, it works fine. Cool. We can take more questions after the next set of slides, just so that we keep moving. Coming to metrics in recommendation systems, it's slightly different from other ML algorithms in terms of like the typical ones that most of you sort of might have interacted with is going to be regression and classification metrics. So it's slightly different. Initially, the research also used these sort of mean absolute error, mean squared error, which is like the difference between the actual rating and the predicted rating. You're just trying to figure out how much error is there. That was like one set of metrics that were used. But eventually people started recognizing, since recommendation systems have this rank list, like essentially when you search something on Google, you won't look through all the results, right? You look through maybe the top 10, top 20 results. So your value or the value of a recommendation algorithm lies in making sure the relevant results come within the top 10. So that's where a new set of metrics very specific to recommendation systems called ranking metrics come into place. So the typical one or the most common one that you could relate is precision. So precision in classification algorithms, hopefully everybody understands how it works. It's true positive divided by true positive plus false positive. So that's a typical definition of precision. In recommendation systems, the only difference is we don't take precision across the entire set. We only take precision at top K, like top 20 results, top 15 results. What is your precision there? Because that is what only matters in a recommendation system, right? User won't go through all your results. It'll go through maybe the top 20, top 25. So precision at K, recall at K, F1 score at K. These are the common metrics you're going to see in recommendation system and in papers. Now, the problem here is that precision, let's say at 10, where, or let's say, let's take this precision at 5. It's 4 out of 5. I mean, 4 true positives out of 1 irrelevant result. So the results going to be 4 out of 5 or 0.8. Now, if all of the 4 were arranged in like consecutive order, like 1, 2, 3, 4. All of the 4, the relevant ones were at the top 4 position versus the relevant ones were at 2, 3, 4, 5. The precision at K score doesn't really provide a difference or doesn't distinguish between both, right? But ideally, when all the relevant results are towards the top, the score should be slightly different, which is where other metrics, and these are the more common metrics used in research papers, come into place, which is like mean average precision at the top K rank. So here, where your relevant result comes in the top K really matters. Like if it's towards the top, what you're calculating essentially is the precision at each K till whatever you're looking at. So precision at 1 is 1, precision at 2 is still 1, precision at 3 is still 1. So your average precision is going to be 3 by 3 or 1 itself. Here, precision at 1 is 1 by 1. Precision at 2 is 2 by 2, still 1. Precision at 3 is 2 by 3, so 0.67. Precision at 4 is 2 by 5 or 0.5. Similarly, you walk down. So this is another way. Here, the relevant results, where they're actually located, matters. And this is one way of making sure that your recommendation algorithm actually starts pushing the relevant results towards the top as much as possible. Now, this is again one way of evaluating your recommendation system. There are a bunch more. A few of them is making sure your recommendations are diverse. So this essentially means that let's say you're recommending 20, a set of 20 items or a set of 30 items. Are you essentially recommending the same thing? Like let's take Netflix again. Are you, if you're recommending 10 movies, are they all Marvel movies? Or do you want to maybe provide some diversity in that? Like if the person is sort of an action hero fan or action movie fan, provide maybe some other movies that are action related. So there are diversity metrics. Similarly, there are coverage metrics. Can you provide recommendations for all users with enough confidence? Is everything in your catalog being recommended at some point or another, or are you just recommending the same top 100 or top 50 items within your catalog? That is also called the popularity bias, because popular items will just get continuously recommended, and people, just because it's popular, may continue to watch it, but you won't let any of the other items pop up in your recommendation system. So do you have enough coverage in terms of catalog and in terms of user? And the most important metric, the online evaluation metrics that you apply during A/B testing, which is click-through rate, conversion rate. These are the ones that actually determine if your recommendation system is impacting the business bottom line. So how many people, based on your recommendations, is deciding to click and like watch the movie or buy the product, stuff like that. So these are the ones that are usually A/B tested on if you're actually developing a recommender system in the industry. So again, most of these, it takes a bit of time to get used to the metrics. I've linked a resource which explains all the metrics, pretty much everything that you'll see in Rexis. And yeah, you'll get this when the slides are shared. Now going into sort of the second gen recommendation systems, these sort of recommendation systems started popping up, I would say, in the later to sort of 2000s, starting with the item based collaborative filtering system. So this was one of those systems that made actually Amazon very effective during those times. uh, an early paper in 2003 came about describing the algorithm that Amazon was using to a certain degree. So till that point, what had dominated recommendation systems was user collaborative filtering. What I had described earlier, where for a particular user, you try to find other users who have similar taste and you recommend what they liked to this user. So that is what dominated because that seemed very intuitive. But the problem was, for websites like Amazon, the number of users that were joining day over day was increasing. And the problem with user based collaborative filtering was a user's taste changes over time. So just because two users are similar right now, it doesn't mean they'll be similar maybe like 6 months down the line. So these algorithms were losing efficacy at certain points in time, and also not able to meet the scale at which users were growing. So because of this, we started switching a bit more to item collaborative filtering. So a very similar idea in the sense that what you're going to do is for each item, you're going to identify items that are similar to it, maybe like the top 20, top 30 items. So if a user has liked a certain item in sort of like the similar set of items, let's say the user has liked item 1, item 3, and let's say this item n minus 1, we want to know if he or she will like this missing item. What we are going to do is we are going to see how similar this missing item is to each of these items, and we are going to average out the score based on the similarity, sort of a weighted similarity. So that's going to give you how much the user is going to like this missing item. Now the advantage of item collaborative filtering is that um, a if you look at the item vector tends to be a lot less sparse than the user vector, because a user might interact with only 10 or 20 items. So in a catalog of 10,000 items, so if you have a vector of 10,000, the user interacts with 10 or 20 items. So only a small percentage is actually has ratings, and the everything else is missing in a sense, which usually is represented by 0. So it's a very sparse vector that you're dealing with. But if you're looking at an item vector, if it's sort of an item that's frequently bought, or a popular item, it has a lot of non-zero values. So item vectors tend to be a little less sparse on average, especially the items that are actually not the niche items, if we can call them. But user vectors, more often than not, tend to be sparse. So because they aren't technically sparse, these algorithms, the item collaborative filtering algorithms, tend to be a lot more accurate. And also the item vector tends to be very stable over the course of time, whereas the user's taste or preferences might change. The item's ratings, if it's a good item, it will continue to get good ratings. If it's a bad item, it will continue to get bad ratings. So the stability of the item's values, and the non-sparsity, both of it lended to the fact that these algorithms were more accurate, or more if more performant than user-based collaborative filtering. And also, since after once an item receives a certain point of ratings, its vector becomes fairly stable. So you don't need to recompute this item collaborative filtering every day or so. You could actually do it like once a day, let it run for 2 or 3 days, then recompute it after like 3 days. So because of this, again, scalability issues were better handled. Now, because of all these reasons, this item collaborative filtering became a lot more popular, and in fact quite dominant in the 2000s. It's pretty much the go-to form of collaborative filtering during that time. Another sort of trend that happened during that time is the collaborative filtering on implicit data sets. So till this point in time, what we were talking about was the ratings. A user actually bought an item or watched a movie and left a specific rating like 3 out of 4 or 5-star review, something like that, right? But the number of times a user actually provides a rating is going to be very small. So um, because of this, researchers wanted to see if they could actually use the implicit feedback that the user give, which is like clicks. Or in YouTube, you don't necessarily like all the videos, but maybe you'll watch a 5-minute video for 1 minute. Some 5-minute videos you'll watch for maybe up to 4 minutes. Some 5-minute videos you'll watch till the end. So the watch duration is providing you a better idea. How much you interact with the product, like on an e-commerce site, do you click the product, do you go through the PDP page, do you go through the reviews? So this kind of click stream data, watch data, all of this is implicit feedback that the user is providing to us on whether they actually like the item, or different degrees of interest in the item. So researchers want to see if it's possible to develop a model using this implicit feedback, and they were actually able to do it. What they did was, all these implicit feedback they handled as binary values. If the user showed an interest, it was 1, or if the user clicked the item, it's 1. If they didn't, it's 0. The more the user interacted with, the more amount of interactions an item received, the higher its score would be till a certain point. So this way they were able to develop certain confidence scores for an item that resembled that sort of acted in a way very similar to the average rating of an item. So this way again they created the user item metrics, and they were able to show that um, this kind of implicit feedback based collaborative filtering could be quite effective. And also this again became a trend of using clickstream data, of using implicit data. This is established like by a paper in like 2008, and again sort of percolated into the industry as well. Another sort of interesting idea that came about this paper, I believe, was that till date, um, no, actually, it's in the next paper. My bad. So yeah, this paper main idea was that the implicit feedback, um, um, till then explicit feedback was what was mostly used. Once this paper was released, more implicit feedback started being used in recommendation systems. Now, coming to the next paper, the factorization methods. So till now, I had talked about like 2 methods of collaborative filtering, which is like the memory-based collaborative filtering, where we use similarity between vectors to figure out what to provide, what recommendations to provide to user. And we have a metrics factorization, or singular value decomposition, either one. Way of breaking down this metrics into 2 matrices, and then using these 2 matrices to bring back the ratings of a user. So there were 2 approaches to collaborative filtering, and researchers always competed with one another on which approach would be more effective, which is like pretty cool to read about in research as well. But this paper sort of did kind of an obvious thing, but at that time it was a bit hard to practically put into implementation, which is that combining both the methods, or what we typically call nowadays as ensembling both the methods together. So this paper actually put together a mathematical formulation of combining both, which worked out very well. It showed that it was more performant than just each of those individual methods by themselves. If you combine those methods, it was more performant. And it also brought about a way of combining explicit and implicit feedback. Again, another way of ensembling data points together. So all of this was proved through this paper, which is called factorization. Factorization machines is like a common word you might hear in recommendation systems, which is nothing but combining the memory-based collaborative filtering and model-based collaborative filtering. Yeah, so that is pretty much Rexis as it is like in the previous decade. Now, before coming to Rexis as it is today, the SOTA architectures, neural networks, and everything, maybe a couple more questions, if there are any.
Yeah, so board is open. Even if you have question, yeah, Akash, just go ahead and ask.
Uh, Hello. Yeah. So previously you mentioned there could be different types of recommender system. Let's say if it is diverse or not, if it is converging a lot of audience or not. So I was just thinking how, like, if it's in development, like if it's a development project, then we just know that it should work like this. Okay, so testing for that is pretty much easy, but how, like, do people test the machine learning models if they are performing correctly or not? So, like, if there some actual job exists like machine learning QA or something. So yeah, so it's not just a pin. There is no pinpoint to get that if it is correct or if it is, I mean, not doing its work properly. So
Recommendation systems is sort of a supervised ML in the sense that what you do is you take, let's say your training data is essentially users and the ratings that users have provided. You will take a small sample of it out based on whatever user and ratings you have. You will try and predict what ratings the users would have given to the movies that you have taken out, and you'll just compare both of them together. The lower the error, the closer your model is, the more relevant the results, the better your model is. That's how we do it. That's how we measure offline performance. And in online, you typically release your product in sort of an A/B testing format, and you try and see, does the recommendation system bring in more clicks? Does it bring in more conversion? If it does, it means your Rexis is performing well. But yeah, it is in fact supervised ML.
okay.
Cool.
Yeah, anyone else? If you have question, just raise your hands. You can just go ahead and ask. Feel free to like convey your message. Yeah, Vishal, you can ask it.
Yeah. So I had just, I mean, it's more sort of a curiosity. If I ever, I mean, if I'm just scrolling or browsing, scrolling through Instagram and I come across a post, and if I just spend, I mean, a few seconds, around 30, 40 seconds, and if I just like keep on scrolling and then spend some time on a particular post or video or whatever it is, then what are the chances of that particular post or that topic getting repeated in my feed again and again?
It's definitely possible. It's essentially, so most companies keep sort of these heuristics hidden, but like YouTube has a certain idea that okay, what proportion of the video should you be watching um, for the user to probably have liked or be curious about those topics further on. Similarly, Instagram has certain heuristics about how much time you should engage with the post or how much of a reel you should watch to maybe recommend that topic again and again. So there are certain heuristics. If you cross those engagement metrics, like let's say a post, if an average a post typically has like an image and a text. So if the text is long, the proportion will be different. If it's like an image with a text, the proportion will be different. But let's say if it's just a plain an image, maybe like 5 seconds, 6 seconds, if you engage with that for more than 5 or 6 seconds, they'll sort of register that okay, this person might like this content. So it really depends upon the type of content. And yeah, and definitely, the more amount of time you spend on certain posts, the more it's likely that those topics tend to get repeated.
Okay. And one more doubt.
Sure.
So if I am talking to someone, chatting with someone on Instagram, and our topic is completely different. Let's consider it's more sort of a depressing topic. Something has happened, and the conversation are a sort of depressing, something like that. So I have noticed many times that the we can fool the algorithm by, I mean, if I'm talking to someone, then after a while I'll get post in the same manner. I mean, I'll get such posts,
Yeah.
same recommendations. So is it more like they are keeping an eye on what we are talking?
What kind of data they have actually access to, it's not really public knowledge. Could be.
I mean, there are very high chances because who knows that what I'm talking and that the algorithm is, I mean, it's recommending the same thing. So basically, they are keeping an eye. I would say, if
Could be, but even if like, I mean, I don't know if it's ethical, but yeah, I mean, even if it's working that way, probably it's not actually looking at your content. Like if you're imagining like somebody reading your actual conversation, that probably isn't happening. Like they'll probably take the text, create an embedding out of it, and those embeddings might work to figure out what topics might be related. But yeah,
like these,
it's not public knowledge. Definitely not public knowledge.
yeah, I get it.
Yeah, just one point I would like to say. Sometimes when we are as a customer, we think that it's
Even
very
I
bad to
noticed.
give data. Yeah. Yeah. Some as a customer, we feel it's very bad to give data, but when we go and learn about data, we feel like okay, we should just steal as much data as possible, and that in fact improves the accuracy of the model. Yeah, Akash, you can ask question if you want.
Hello. Yeah, I was just thinking, can the learning from one platform can be used in another platform? Let's say if I'm creating a new platform that where I sell movie merchandises, and here, since it's a new platform, there's not a lot of users to so that my machine learning model can actually learn from. So let's say if I have some access that how Netflix's machine learning model is performing, so can their current learn what they have learned can be used in our application so that we know what the current audiences needs, like what they want, what they like, and what they don't like, so that I can optimize my platform. So is it possible or not?
There are definitely companies that are trying to do this, primarily because like a lot of like e-com sort of shops are sort of opening up, and they would like to tackle what we call like the cold start problem as much as possible. The current SOTA algorithms work a bit more on IDs, so it would be hard to shift between companies because if you each item has an embedding. So let's say Netflix Marvel movie, or Netflix, let's say a set of movies. If another streaming service has the same catalog, and you can map it, the like movie embedding one by one to whatever their catalog is, then maybe yes. But I would say it's a bit tricky. There are definitely like startups and companies that are trying to do this too.
Okay.
Just like so the idea would be very similar to like language models. It has like world knowledge built in. Similarly, recommendation systems that has like world knowledge built in. And yeah, LLMs and recommender systems is also something that's recently started trending. Yeah. But yeah, in the interest of time, third gen recommendation systems. If you guys have questions, definitely we can take more after this section as well. So third gen. So yeah, late 2000s, we saw an uptick in deep learning and cloud computing. So that led to two trends. One, because of cloud computing, compute and everything became a lot more cheaper, and deep learning became a lot more viable. So this led to two main type of architectures in deep learning. One which we call the wide and deep neural network, that was proposed by Google, and then the two tower neural network. So a quick overview of them. Wide and deep neural network, the idea is it has what we call a wide component, which is nothing but any feature that you want to feed into the model. Those features are essentially allowed to interact with one another in a very shallow layer, which is like shallow layer, meaning that there's only like one layer in your neural network, and you just allow all your features to come and interact in that layer. That's called the wide network. And then it has a deep component where all the features pass through like a multi-layer deep neural network. And the idea or the intuition behind it is that this wide part will memorize will sort of have a short term memory, and the deep part will try to find patterns or try to generalize better. This is because if you have a neural network that gets like progressively deeper, or has like multiple layers, it tries to extract patterns better. But a shallow one just memorizes the most prominent pattern. So let's say, again, coming to like the Netflix example, the user watched like three Marvel movies in consecutively, one after another, or like it's Christmas, maybe people watch like went on a Harry Potter marathon, like three Harry Potter movies one after another. So those short-term memory it will leverage to try and maybe predict a bit more of those sort of fantasy drama films. Deep learning, it will maybe look at higher level generalizations and try to provide recommendations based on those high level abstracted patterns. So that's basically wide and deep network. This architecture isn't as popular, I would say, in the industry. The more popular one is two tower neural network. So two tower, because we have two neural network towers, one for the user. So in this you pass in the user's id. Each user will have an id in your in the backend, and certain user attributes as well you can pass, like maybe demographic attributes. If it's a more specific system like a social networking system, you might have more like age, specific location, some maybe some things like likes or songs or movies that they like, stuff like that. So you could also pass those attributes into like a deep network. And similarly, you have an item tower where you pass the item id. Item id again remains the most important feature. Like most research has shown that the id feature is like contributes like 60 to 70% of the accuracy or importance. So item id, and then whatever item attributes you have. So both of them pass through their own deep neural network. And finally, you try and see how similar this item is to this user. Similar might not be the right word, but we call it similar because it's cosine similarity that's being used. The idea is this neural network is trained in such a way that the final user and item embeddings are produced, so that if the user likes an item a lot, the user embedding and the item embedding tend to be very similar. So the back the neural network or the back propagation trains in a way to produce embeddings that are going to be similar from the user tower and the item tower. And this is a common architecture. Like there is a paper for YouTube that came out, I think in like 2012 or so. They talked heavily about using this two tower neural network as well. So yeah, these are like two core architectures that became very common. And another one that became common is the graph recommender system. So till now, whenever we look at um, how we provide recommendations, we are talking about if the user interacted with a certain item. So we aren't really taking the context of how the user reached that item. So what graph recommendation systems hypothesize is that the sequence of interactions that led the user to that item. Let's say you're scrolling through Netflix, you saw maybe a few movies, you didn't like them, maybe, but you saw a movie that you like, but you watched previously. From there, you went into like similar movies. So that journey is sort of important in providing the next recommendation. That is what graph recommender systems hypothesize. And what it's doing is nothing but considering each node as an item and an edge if the user has come from that item, from the previous item to that item. And what it's trying to do is it's trying to get sort of like or represent a particular item by its own features and by features that led the user to this item from a previous item. And the idea is to embed context into each item's embeddings. And hopefully, if let's say a user left off a journey at they were going through, they were shopping on Amazon for like Christmas gifts, and they went through a bunch of like let's say games, couple of board games, couple of card games, but they eventually dropped their journey. They couldn't find what they wanted. That journey might help provide the next recommendation, that okay, they went through board games, card games, maybe some kind of strategy games could be a next recommendation, because other users who have gone through this journey have reached there, and they have made purchases. So the context of the user journey could be leveraged, is what graph recommendations is stating. And Pinterest popularized this through one of their algorithms called graph sage. um, but yeah, these are like the three common architectures you're going to see in research. And there's a lot of like mixing and matching. People use multiple architectures together, but these probably are going to be the most common names you're going to see. And for each of them, how to get started, like maybe implementing a wide neural network, two tower network. If you're interested in recommender systems, I would say start with like simple collaborative filtering, and then if you want to move into the advanced portion, go for a neural network is going to be my recommendation. And like some code examples and GitHubs that will help you get started. All of it's linked in the slides I'll send over, so anybody who's interested can get started. And yeah, maybe ending with what is state of the art currently. So state of the art currently, recommender systems don't work as a single output model. Currently, most recommendation systems are divided into a couple of phases. The first phase is what we call candidate generation. The next is a ranking, and then there could be other phases like re-ranking, etc. So what happens is, like, since recommendation systems in this day and age deal with like millions of users and billions of products, the kind of compute necessary is significant. So, which is why they divide it into multiple phases. So, what happens is, in candidate generation, you might be dealing with millions or billions of user items. So, this phase maybe runs once a day, and for each, let's say, item, it sort of figures out maybe hundreds of similar items, or for each user, it provides maybe hundreds or thousands of recommendations that can be made. Then the ranking phase is something that could be run hourly, sub-hourly, etc. Based on the candidate generation, it's going to filter out based on the immediate interactions the user is making, maybe during their live session. What are they interacting with? Okay, because between shopping sessions or viewing sessions, your taste might have changed. Like yesterday night you watched something like a Bollywood movie. Today you might be looking through Hollywood movies, so you don't want to stick to the same recommendations you made based on the immediate session. You want to take information and adapt quickly. So that's where ranking comes in. The immediate context is injected to filter all your recommendations and provide more relevant results. And after this, there could be even more stages like re-ranking. This is typically a bit more common, I would say, in e-commerce systems, where, let's say, it's annual events like Black Friday. They have a lot of sales going on, so they want to make sure these sales sort of start popping up in recommendation systems. So it's a bit more driven by sales, marketing, all of those things. So those business logic comes in to re-rank the recommendations that are made, to push items that they want to be sold, stuff like that. So this is how current state recommendation systems work in. And if you're going to be working in the industry, you'll be working in one of the teams that manage one of the models. Like, you could be working on a candidate generation team or a ranking team, or more commonly re-ranking teams, because there's a lot of re-ranking logic. Usually there's only one team working on candidate generation, multiple teams working on re-ranking based on different business use cases. And yeah, how to get started. TorchRec is a good sort of like very similar to TensorFlow, PyTorch, etc. TorchRec is like a good package to get familiar with for like experimentation. Like in the industry, you're going to be mostly using TensorFlow. Baseline data set is movie lens, and I've like linked a couple of papers you guys can go through to get a better understanding of the field as well. And what current challenges are researchers or industry folk working on. One is multimodal data, like user interaction data is one thing, text data is another thing, but now we have a lot of visual data, social network data, etc., that are being injected. So how do we actually use all of this data to create one single embedding? That's a very interesting field. The other one is sequential or user intent sessions. Like each time a user logs into maybe Netflix or Amazon, they have a specific intent, trying to see if that intent relates with the immediate prior intent, or do we want to refresh and start looking at this session completely separately from the prior ones. The identifying user intent and figuring out how to switch recommendations based on that, that's a very interesting field. Re-ranking for business logic, that's a very common problem that you'll be working on if you're in the industry. Different businesses have different motivations that they want to have reflected in their recommendation systems. So that's going to be a very common problem if you get down in recommended systems, that you'll be working on. And last and most importantly, bias and explainability. There's a lot of bias that can come within the systems, specifically popularity bias. You tend to recommend just the popular items, rather than help users identify items that could be helpful to them at like a good price. But there could be items that exist like that, but you tend to recommend popular items. Popularity bias is a very common one. And explaining why a recommendation was made, that's quite tricky, especially since multiple systems are involved. So providing more transparency, all of that, that's also an interesting challenge, both in the research space and on the industry side of things. And yeah, I think that's pretty much all I had in mind to cover. Don't know if I left enough time for questions, but yeah, I can take any questions if there are.
Yeah, so I have a question, but if any one of you have any question, you can just go ahead and ask. I might ask mine in the last. I think you guys might be very tired. Some of you might have not even learned about some of the topics he have taught, but we will definitely share all the links provided so that you understand the session in depth later on. So it's just my question, Garun, a simple question that I want to ask. Let's say there are two products, bread and butter. Okay. So, and there are two couples, husband and wife. So if the wife goes and buys milk and they are coming to back to the same household, okay. So will the suggestion for the bread will be shown to the husband?
So yeah, if they're both tagged with the same user ID, let's say my wife uses my Amazon, so her sort of like shopping recommendations will pop up on my screen. If they're tagged with the same user ID, it will show up on my Amazon feed as well.
Okay, so is it just item to item recommendation system that is, I think, used by Amazon, item to item recommendation system?
Um,
Uh,
it was used in like 2003. It got popular because of how efficient it was for Amazon. But yeah, nowadays, what's exactly used, it wouldn't be public knowledge.
okay, they have like made it their own. Yeah, yeah,
Yeah.
definitely. So it was a wonderful session with you, Garun. I think I know you from much behind. Like I have learned a lot of things from you, and I guess a lot of these people might go and like follow you. Just go and follow him on LinkedIn. You guys might see some amazing research that is going across the world, and he also offers some mentorship. You can also look for that. He's an amazing guy. Has taught me a lot of things. Okay,
Thanks.
so it was great to have you here. Yeah, Subrat, if you have question, you can just ask.
Hello, good evening, sir. It was a wonderful session, though I did not understand a lot. But I
Sure,
just
sure.
had a very simple question, and like I just wanted to know, because you are like so knowledgeable and you have so much experience. As a beginner, like what are the ways to get entry level jobs in this field of data science? I mean, I don't have any problem with researching and doing a lot of studies and project to get into the job, but I just want to know like how to just get an entry into the field, and then while you are doing job and supporting yourself, you can do all the research and project work. So
For sure, yeah. Data science, like I have like a roadmap on TopMate that you can check out. But basic skills that you need to land an entry level job is going to be a bit of data structures and algorithms. Leak code medium is what you need to prep for. SQL is a must. Most interviews are going to have like SQL. So these are the initial filter criteria. You need to pass this, even though like day to day we don't use a lot of DSA. It's still sort of like a filter criteria still. So DSA and SQL, those two, make sure you're good with. Then from a machine learning side, a bit of ML theory, the foundational models you need to know. Introduction to Statistical Learning in Python. It's a book that's free. You can check it out. It's sort of a very solid book in making sure your foundations in machine learning are good. I'll actually drop the link if I can find it. Uh, So yeah, this is a book to make sure your foundations in machine learning are solid. And deep learning is sort of a requirement nowadays. So this book by Ian Goodfellow is sort of the person who invented generative adversarial networks, and he sort of started this generative wave. Yeah, so his book, he breaks down concepts very well. So it's also a good textbook. It's again a free textbook. So yeah, DSA, SQL, machine learning, and knowing a bit of stats is good. There is a good book called, I mean, ISLP teaches you a decent amount, but probability for data scientists, there is a book. Um, Again, let me just drop the link to my top mate. I think I've linked all the books in that guide, so you can just check that out. The guide is like free to download. So yeah, here you go.
Thank you.
So yeah, it covers like DSA, SQL, statistics, ML, So once you have like your foundation ready, then it's basically about having a good set of projects. What projects work for entry level? That's also there in a guide. Blueprint to increase callbacks. What I feel works for an entry level role is having a forecasting project, having a large scale data science project on PySpark. Like everyone who has a student account gets like AWS free to a certain extent for I think a few months still. So a large scale data science project and some kind of like Gen AI project, just because there's a lot of hype around that, showcasing that you know it is good. It doesn't have to be necessarily a Gen AI project. An NLP project will also work. So yeah, these three projects, if you have on your resume, I feel like can increase your chance of getting a call back. And yeah, you're all IT folks, so just make sure you leverage your alumni and leverage your network to get those referrals.
Yeah, yeah. Thanks, thanks.
Yeah,
Okay.
Akash, I think you should quickly wrap up. Madhurya, you say, go ahead. Akash. Let's just ask. Let Maria ask. Okay, you have asked your questions. Okay, it's better.
This might be a bit of an off topic from the session. So so I am also doing a master's in data science. So I just wanted to know, like, some of the courses that I covered actually focused on a lot of introductory level math and stats. So how much would that as a skill help me, like, or focusing on that help me in getting over the basics of ML and DL properly. So if I have some, I feel that I lack some knowledge in those basics. Is it going to have a good effect, or should I focus on learning more advanced things, or focus on the foundational part that's there?
So I guess the best way to answer it is in terms of like landing a job. So in terms of landing a job, there are two hurdles to cross. One is like getting that initial callback, and second is clearing the interview. So what lands you the initial callback is going to be the quality of your project. So irrespective of your knowledge, if you have done good projects, like irrespective of how sound your fundamentals are, if you have done good projects that have business relevance, that's why I said forecasting has business relevance. Large scale prediction, very common in the industry, has business relevance. Gen AI or NLP related projects getting more business relevant. So if you've done business relevant projects, and if they are written on your resume, you have a high chance of getting a call back. So even if you don't know a lot of foundations, it's fine. Make sure you do good projects. In terms of clearing the interview, typically you're going to have an ML basics round where they're going to ask questions like, why is randomization important in random forests, or what are the assumptions of linear regression and how do you test for them. So those questions are going to be asked, so you need to be able to answer them. So at that point, brushing up on your fundamentals does become important to a certain degree. And like I said, ISLP is a great book for that, and probability for data science is a great book for that. Now, if your question is regarding the day to day of data science, um, more often than not, you can. I mean, like most people Google stuff, and you can just figure things out on your job as well. So I wouldn't say a strong foundation is required, but like a basic idea of, okay, a model has certain assumptions. I should know these assumptions. I should know how to test for these assumptions. How do I fit and tune a model? How do I evaluate performance? Those basic ideas you should have. That's about it.
Okay, thank you. Thank you for your time. Yeah.
Yeah. Yeah. Okay. I think we will be skipping the questions now, Akash. Okay. I think we need to wrap up the session. It's already been very long. So I will hand over to our Deputy Secretary Madhur. He will be concluding the sessions, and we can of course have a session ahead as well in case you demand for something like I have already discussed that with the Karun.
Yep.
Okay, yeah,
Yep.
Madhur,
Okay.
yes, go ahead.
uh, I would say whatever sort of in terms it depends again slightly on what your goal with research is. If you're looking to invent the next best thing in recommender systems, either is fine. If you are looking to land a huge high paying job in like a fan company, then probably exploring a bit more might be better. For sure, for sure. The basic idea or what helped me the most primarily is making sure I have a mechanism for continuously like reading and engaging with research. One quick way is making sure you are a reviewer for a couple of journals. It especially like since all of you are like IT folk, it's pretty easy. Just apply to a few journals saying that you want to be a reviewer. Um, Apply to maybe like 20 or 30. That way at least once a month you'll get a paper to review. That will sort of keep you inspired and sort of motivated to stay or continue researching in the field. That's a mechanism that I often use. And the other one is like make sure you have a target of that. Okay, at least one paper a week. I'm going to read at least one paper a week in my field of interest. And it doesn't have to be a very tough paper or a very hard paper, but it can be a paper that you're genuinely curious about. So just take at least one paper a week. So these two mechanisms, review and read, this is going to probably make sure that you have like a very solid research career. Definitely, definitely.
Yeah,
It was a great session.
yeah,
Yeah.
yeah,
Thank you so much, sir.
Thanks all. Bye.
yeah, yeah. Thank you, sir. Okay, we will have a session. Okay, yeah. Yeah, so everyone, so I hope you guys might have enjoyed the session, and it was a wonderful to have you, so many of you, for so long. As a research society, we are planning to build the group of researchers who can actually represent IIT Madras for the future uh, endeavors, I would say. So it would be great if you guys just come forward